So this will serve as a brief Cliff Notes version to the Cliff Notes version to the Cliff Notes version to the Cliff Notes version of chemistry. Hopefully get you started. I like to start with this picture of a periodic table that's actually a wooden table that's made by a guy named Theodore Gray, who collects all the elements. This is a good place to start just because it's kind of cool. He actually made the table, and then this little wood piece will come off of here iron, and you can look inside and see some iron, which doesn't sound so cool about iron, but if you take off the one for mercury, you can see mercury, gold, you can see gold, and xenon. You can click on them and come back and see it if you're interested. His name is Theodore Gray. He wrote has an awesome book about all of his element collection, and then the website's pretty handy too. So, at any rate, we'll start with chemistry. To start chemistry, you have to understand the subatomic particles. And inside this is going to be all by web pages because I don't have my document camera. All atoms have what are called subatomic particles: protons, neutrons, and electrons. Protons and neutrons are both inside of the nucleus. Protons are positive, and neutrons are neutral, meaning they don't have a positive or a negative charge. The electrons are outside of the nucleus in what are called electron shells or energy levels, and they have a negative charge. They're abbreviated with an E with a little negative sign as a subscript, or a superscript up here, rather, sorry. So, subatomic particles you've got to understand: protons, neutrons, and electrons. So going into protons, neutrons, and electrons just a little bit, protons are what we call the fingerprint of the atom. The number of protons tells you what the atom is. End of story. If it has 1 proton, it's hydrogen. If it has 2, it's helium, 3, lithium, so forth and so on. That cannot change. If you change the number of protons, you have changed what atom it is. That's as opposed to the neutron and the electron. You can actually change the number of neutrons and get what's called an isotope of the same atom. So you have a different isotope like uranium. You'll have different isotopes of uranium based on the number of neutrons that are in the nucleus. It's still uranium because it still has the number of protons for uranium, 93, I can't remember off the top of my head. But the number of neutrons can change. You can change the number of electrons as well. When you change the number of electrons, you get what's called an ion. You can have a positive ion when it loses electrons, or a negative ion when it gains electrons. We'll talk more about that later. But at any rate, electrons can change, neutrons can change, protons, they stay the same. That's why we call it the fingerprint of the atom. So, and then if you're trying to figure out what this all means, when you're trying to look at an atom, you look at the periodic table, you will look at an element square. Oops, let me get to I need one more screen here. And so when you look at the periodic table, you're going to see an element square that looks similar to this right here. Here's the one for zinc, and it has a couple things that you need to know about zinc. This is your symbol, Zn, obviously. There's a smaller number that might be usually in the top left, sometimes in the top center, but you got to use the key on the periodic table because they show up in different spots. But this smaller number is what we call the atomic number. The atomic number identifies the atom because it tells you how many protons are in that atom. So for instance, zinc has 30 protons. So this number is established, set in stone. The larger of the two numbers is what we call the atomic mass. And the atomic mass for what we're going to do in basic chemistry is you're going to say the atomic mass is the number of protons plus the number of neutrons. Now the reason that's the number of protons plus number of neutrons is because it's only the protons and neutrons that have mass. We say they have each of those has an atomic mass unit of 1 AMU. Whereas an electron has 0 AMUs as its mass. Technically, the electron has some mass, it's just very little mass. It's kind of like I said, if you stood on a bathroom scale and somebody handed you a hair follicle, would your mass change? Yeah, technically it would, but is it worth talking about? Not really. That's sort of the situation we have with electrons. Electrons have so little mass that we have, say, 0 AMUs. So, 65, if a proton has 1 AMU, and a neutron has 1 AMU for each one, that means you have 65 things in the nucleus. If you have 65 things in the nucleus, we said from the atomic number, 30 of those things are protons. So there's 65 things in there, 30 of them are protons. If we go back and look at a subatomic particle, the things that are in the nucleus are protons and neutrons. Well, if there's 65 things in there, 30 of them are protons, that means 35 have to be neutrons. So we can establish how many neutrons are in the nucleus based on the atomic mass and the atomic number. So to get your protons, you look at your atomic number. To get your neutrons, you do the atomic mass minus the atomic number. Now, you'll see a decimal there. That's because isotopes, I basically skipped that with my intro-level chemistry students because we haven't talked about isotopes yet. It's not worth talking about. Basically, as you change the number of neutrons, it changes the amount of mass. Some of them show up more often than the others. This is a way to average that, to say this is, on average, this is what the mass looks like. So, but for us, to get neutrons, you do atomic mass minus your atomic number. The only thing we haven't talked about is electrons. So the way that you get the number of electrons that an atom might have is, to start off, you say that all atoms are neutral. So the number of protons, which is positively charged, is equal to the number of electrons. So if we have 30 positive charges, to make it neutral, we have to have 30 negative charges. Electrons are negative, so we would say we have 30 electrons. So by looking at this square, we can say zinc has 30 protons, 30 electrons, and it's going to have 65 minus 30, which is 35 neutrons. And so now we know how many subatomic particles are in that atom. That's the first step. Once we have that, we can build what's called a Bohr model of an atom, and students seem to like this because it's pretty concrete in terms of setting it up. And so a Bohr model, named after Niels Bohr, you basically just start with, pull up here, sorry. I'll just go back to it. It's a way of drawing the atom to show where the subatomic particles are. So you can draw the number of circles. I have my students write here they'd have 3p, maybe 4n, and then 3 electrons. So I just, in the nucleus, instead of trying to draw your different colored protons and neutron circles, I just put the number and then a p and the number and then an n. It makes it a little bit easier. Kind of like you see right here. So they have 13 positives, 14 neutrals, and your electrons around the outside. There is a systematic way of drawing these electrons. Electrons can only go on shells. As you move along in chemistry and into some modern physics, you can realize that these are like rungs of a ladder, and so the electrons can move to a new energy shell, but they have to have energy, so forth and so on. I won't get there. But really, for placing the electrons, all that you have to do is you have to sort of memorize this first little way. You just have to memorize this. 2 electrons fill up the first shell. So if we have to place, in this case, we have 13 electrons. So we have to put 13 electrons. We know we have 13 electrons. We have 13 protons. So we have to place 13. The first shell can hold 2, top and bottom. And I have my students go top, bottom, left, right, top, bottom, left, right. I encourage you to do the same. It'll help down the road. So top and bottom are your first shell is full. Then we have 11 more we still have to place. So we have to go to the next shell. So now we have 1, 2, and then we're going to go top, bottom, left, right, and now we've added 4. The second shell can hold 8 in that shell. So we put 4 there already, so we're going to go top, bottom, left, right again, so that each of those spots, the top, the bottom, the left, and the right, are all paired. So now we have 2 on the first shell and 8 on the second shell, which gives us a total of 10. We have 3 more that we still need to place. So we go top, and this image did top, left, right, which is fine. But as you see, so on the outer shell, there are only 3 electrons. So this is a good point to practice this, and so kids, you can give them an element square. They can figure out how many protons, neutrons, and electrons it has, and then they can go and draw this little Bohr model. They tend to like that. I often have students do it on like a little circular piece of paper, and then after we try and do all the elements on the periodic table, and then we can hang them up in order of the periodic table and see what I'm going to show you next. So it's sort of up to you. But this is called a Bohr model, It helps show the structure of an atom. Once you have the Bohr model, so if you have a bunch of people doing, and really I only talk about the first 3 shells in an intro chemistry class. After that it gets a little bit trickier, but not too bad. But if they can get this idea, that's a good enough foundation. So once they have the Bohr model, you can start to look at the periodic table. And we know that the periodic table is not just some random assortment of elements after you do the Bohr model. Because if you go through and you do all these Bohr models, you'll see some trends. And the first trend that stands out is if you look at the outer electron shell only. So if you do hydrogen, you look at the outer electron shell, you'll see that it has 1 electron in that outermost shell. We call that the valence shell. That's the most important shell. If we're looking at this Bohr model, what we find out is that these inner shells don't really matter. The one that's important is this outer shell. It's called the valence shell, and these are called valence electrons, electrons in the outermost energy shell. And we realize, by looking at if we can do a ton of these and put them up in the order of the periodic table, that the number of valence electrons tells you which column or which family it's in. So the periodic table is organized so that all these in the first column, the first family, which we call the alkali metals, they all have 1 valence electron in their outermost shell. Now, there's a bunch of shells. There's 1 shell here. This one has 2 shells, lithium. This one has 3 shells, 4 shells. And so you see another trend here that we'll talk about in a second. But first thing I want to point out is that the columns are organized by elements that have the same number of valence electrons, or electrons in the outermost shell. The first column, they have 1. The second column, they all have 2 valence electrons. I skipped the transition metals, which are actually right in here. They're not shown on this. They don't really play by the rules, is what we say. So we say, we'll skip them, we'll get all these other ones, and we'll come back and talk about the transition metals later if we have time. So skipping the transition metals, all the way over to the boron family, these all have 3 valence electrons. These all have 4 valence electrons, 5, 6, 7, 8. 8 means it has a full outer shell, or a full octet. That means it's totally stable, it's not going to react. So these valence electrons are important because they tell the reactivity of the atom. Things want to have a full outer shell. So these guys have a full, and so the example I use is an 8-person basketball tournament. If you have 8 people, if you have to have 8 people to play in the tournament, and these guys show up and they have 8 people, they're happy. They're not going to take any extra players. They're not going to give anybody away. They're satisfied where they are. If you look at these guys, these are called the halogens. The halogens have 7 valence electrons. So I say, imagine if you showed up at an 8-on-8 basketball tournament and you only had 7 people. You would really much want 1 extra player, right? You don't care if the player's good, bad, ugly, mean, whatever they are. You want a player to fill that shell. So these are very reactive right through here because they're really close to having that full shell. So they really want 1 extra person. So very reactive. And as you move back this way, they're a little bit less reactive. Until you get over here, right, these guys show up and they just have 1 extra player. So I say, well, what about these guys? Is it easier to find 7 other players, or for you to say, let's take that 1 player and go find another team? And students are pretty quick to realize that you just take the 1 player, go find another team. So look, you can imagine what might happen here. These guys have 1 player looking for another team. These guys are missing 1 player. So what often happens is this electron can go here. And so sodium likes to bond with chlorine. It will give that 1 electron to chlorine because if you go back a shell for sodium, the previous shell is full. That's why I had to go to this outer one. And so then they'd have a shell of 8. So sodium would be happy. Chlorine would have a shell of 8. They'd be happy, a full octet. And so sodium bonds with chlorine. So we get NaCl, sodium chloride, which is table salt. Sodium chloride is an interesting thing that I often talk about because sodium is poisonous alone by itself. It'll kill you if you take too much of it. Chlorine, poisonous alone by itself. If you take too much of it, you can die. However, if you put them together and make a chemical change, it becomes tasty when you sprinkle it on your French fries.